All right, so the first idea we're going to look at is this idea of partial fractions. So the idea is whenever we want to integrate polynomial on a polynomial. So that sort of one. Now, if the degree of the numerator is more or equal to the degree of the denominator, then do a polynomial division first to break up the fraction. Okay. And once it's less than, then we'll factorise that denominator. And then how it factorises will tell us how we're going to break up the partial fractions. So, in the denominator, if there is a linear factor when we factorise, then we will create a fraction, some constant number over x minus a. So basically we're creating a fraction where the degree of the numerator is 1 less than the degree of the denominator. So if it's a linear factor on the bottom, I'll create a constant on top. Now, if it's a multiple one, what I do is I create a fraction for every one of the powers. So I'll have 1 for x minus a, 1 for x minus a squared, and so on and so on and so on, up to whatever the highest power is. We're probably only ever going to see ones up to the power of 2. They don't tend to go much further than that. And then if it's a polynomial factor, but if you think about it, because remember we've seen that everything can be factorised down to a mixture of quadratics and linears. So it's only ever going to be a quadratic, the other factor. Then on the top we would create a linear function on top, the degree 1 less than the bottom, so ax plus b. So I want to integrate, we'll start off with something rather simple, x squared on x plus 1. So I'll do a polynomial division if I have to. You might be able to look at it and go, oh, I know how this is going to break up. But we'll end up with, there we go, and the remainder is 1. So I could rewrite that as x minus 1 plus 1 on x plus 1. Now in this case, I don't have to do anything else because everything there we know how to integrate. Right? The x, obviously the 1, and then I've got a log function here in the 1 on x plus 1. So that becomes half x squared minus x plus the log of x plus 1. Let's try one where we've got to do some factorising. This one's okay because the numerator is a constant, so I don't need to do a polynomial division. If I factorise the bottom, it's simply x outside of x minus 1. So I'm going to create 2 fractions. One for the factor of x, one for the factor of x minus 1. So some constant on x plus some constant on x minus 1 will give me the answer. What we're basically doing is the reverse of those algebraic fraction questions. Where normally if we had 2 algebraic fractions, add them together and would make 1 fraction, we're going back the other way. So we know what the denominators would be in that question, the x and the x minus 1. The question is, what is the numerators? So how do I work it out? Well, basically, get rid of the denominator. And so I've got now this equation to solve. And this is just like we've seen in quadratic identities and things like that. The coefficient of x must equal the coefficient of x, the constant must equal the constant. That's one idea we can use. We can also use substitution to do it as well. So first thing I'm going to do is I'm just going to substitute in x equals 0. And the reason I chose 0 is because it'll get rid of b. And I can work out a straight away. So sub that in and I get negative a is 3. So, okay, a is negative 3. Now I could substitute in x equals 1 and I'll get rid of the a straight away. And so that just gives me b is 3. So I now know what those constants are. So I can rewrite my integral now. I know that will be minus 3 on x plus 3 on x minus 1. Both of those are log functions. So I get minus 3 log x plus 3 log x minus 1. But remember, if the coefficient of the log function, and I'm just talking about the size of the number here, I'm not worried about the plus or minus, is the same, we tend to bring it together using our log laws. So I'm going to rewrite that as 3 log x minus 1 on x. I suppose if you wanted to, you could even bring the 3 in and write it as the log of x minus 1 on x all cubed, but don't tend to do that. Again, I don't have to do a polynomial division on this one because I've got a linear function on top, a quadratic on the bottom. So if we factorise the bottom, I get 2 linear factors. So I'm going to set up 2 fractions, but then multiply out, get rid of the denominators. Let's see. Well, again, I can just use clever choose a substitution. I'll make x equal negative 2. That'll get rid of the a. So b is negative 3/7. X equals 5, that'll get rid of the b, a is 10/7. So I can rewrite my integral. I suppose I could have taken 1/7 out as a common factor there to tidy it up a little bit. But anyway, once again, we've ended up with log functions. So I've got 10/7 the log of x minus 5 minus 3/7. You'll notice here I haven't bothered using my log laws. I mean, it would be possible to put those together, but too much fiddling around. I'm not going to worry about that one. Okay, if I factorise that cubic, I'll get x squared plus 1, but x squared plus 1 does not factorise. So when I set this one up, I've got one which is linear, that's the x, but one that's a quadratic. So on the top, I'll create bx plus c. So again, we now have to find a, b, and c. I can again use substitution, because I can make x equals 0, and that'll get b and c to disappear. I can work out a straight away. So let's do that one. A is 1. Now, how do I make the other bits disappear? Well, there's nothing stopping me using complex numbers. If I make x equal to I, then a will disappear. And I end up with minus b plus ci is equal to 1. But the real part must equal the real part, and the imaginary part must equal the imaginary part. So therefore, b must be negative 1, and c must be 0. Okay, so let's use what we've learned. We've learned about complex numbers. Let's use it to our advantage. And so there's my fractions. We get 1 on x minus x on x squared plus 1. Again, they both turn out to be log functions because the derivative of x squared plus 1 would be 2x, of course. So we've got a multiple there. So I end up with log x minus a half of log x squared plus 1. Let's do one here where I've got a quadratic factor and I've got a repeated root there. I've got x plus 1 squared. So the way I like to do these ones, okay, I set up a factor for each of those powers. So I've got one fraction x plus 1, one fraction x plus 1 squared. And then I've set up another one for the quadratic, the x squared plus 1, cx plus d. Now, the reason I do it this way, I could have just done one there and could have on the top, because it's a quadratic, gone, oh, well, I'll make that bx plus whatever, which is effectively the same as doing that, because if I was to combine those two together, then the a would have become ax plus a, and so on. But this has the advantage of splitting it into two fractions straight away. All right, whoa, clever use of substitution, hey? What shall we substitute in? What did I do first? Negative 1. Ah, yes, because that makes the first bit disappear. It also makes the last bit disappear as well. So I get b is negative a half. I then did x equals I, so the x squared plus 1s will disappear. Over here, 1 plus I squared actually works out quite nicely. What's 1 plus I all squared? It does turn out to be 2i when you think about it. Because it's a perfect square, you're going to get I squared, twice the product, but then you're going to have 1 squared, and I squared and 1 cancel out. So that I plus 1 actually is quite nice. And then we get the minus 2c plus 2d. So balancing that out, I now know c equals 0, d equals a half. I still have to work out a. Oh, well, I'll just make x equals 0. I'm going to end up with something I got to substitute into, but I've worked out what b and c and d are, so it's not a hard substitution. So I make 0, because that's easy to substitute in, and I end up, a actually turns out to be 0. Another way I could look at that one, which is so large, is the idea of identities again. I could say something like, well, I know the coefficient of x cubed must be the same on both. So what would produce x cubed? I'd have an ax cubed from that one. There'd be no bx cubed here, but I'd have a cx cubed in this one. So I know a plus z must equal 0, because there's no x cubed. So I can combine different ideas to find those. All right, so let's have a look at what we have to integrate. We got things that aren't going to be log functions. I've got minus 1 on 2x plus 1 squared. Well, that's just x plus 1 to the negative 2, so that's a standard add 1 to the power over the power. And then I've got x squared plus 1. That's our inverse trick, inverse tan. So we end up with, there we go. Let's make it look nicer. There. I've left half out as a factor. Well, it doesn't really matter. there is an alternative way for finding the constants. If the denominator turns out to be all constant factors. So if I want to find a, I'm going to substitute little a into the function on the right-hand side. But you'll notice on the right-hand side, I've left out the factor x minus a. So, right? So it's capital A that I want to find. So I say, well, what makes x minus a equal to 0? Oh, a would do. So that's what I'm going to substitute into the right-hand side, but less the x minus a factor. So it'll become a minus b, a minus c, a minus d, and so on and so on. If I then want to find b, same idea. Well, what makes the x minus b equal to 0? Little b does. So in the right-hand side, I'll substitute b, but I won't use the x minus b. And it's sometimes called the cover-up method, because it's like saying, well, I'm going to cover up the factor that I'm not going to substitute. Oh, that's what I substitute into. So the next one, x minus b. I'm going to cover up the x minus b, pretend it's not there, substitute into the rest. So I want to find c, then I'd say, well, what makes x minus c equal to 0? Well, little c would. So in the other side, I'll cover up the x minus c, substitute c into everything else. And so on for however many factors you've got there. So, all right, let's go back to this question that we saw. I won't bother integrating it, of course, because we've already done that, but just to show how we'd find the a and the b. So, if I want to find the a, I look at the denominator. What would make the denominator equal to 0? Well, 0 would. So I substitute that into the right-hand side, but that factor of x is no longer there. So I substitute into 3 on x minus 1. So a will be negative 3. So we can do the same with the b. What would make the denominator equal to 0? Oh, 1. Okay, go to the other side, cover up the x minus 1. I'm going to substitute into 3 on x. So it is quite quick. It is quite quick. All right, so then here was another one we looked at. Okay, so same idea. We're going to find a. What would make that equal to 0? X equals 5. So I will substitute it into the right-hand side, but I will cover up the x minus 5. So I'm going to substitute it into x plus 5 on x plus 2. So the a works out to be 10 on 7, which is what we got before. I want to find b. What would make it equal to 0? Oh, well, negative 2 would. Substitute in negative 2, and then sure enough we get minus 3 on 7s. So, all right, so that method's great, but it relies on all the factors being linear. So when I looked at this idea, I thought to myself, well, surely we can extend this idea out for any factor. So if I use complex numbers, then it will work for quadratic factors as well. So here was our next one. Remember, the basic idea was, what makes the denominator equal to 0, then cover up that factor. Okay? So the a, I can still do. So the a is going to be 1. But what about the other one? I look at that denominator, x squared plus 1. What is going to make that equal to 0? No, there's 2 possibilities. Right, and that's where we've got to think of x squared plus 1 as 2 linear factors. X plus I, x minus I, and then we could do it like the method before because we've now got linear factors. Okay. So when I substitute it in, cover up, I don't have to actually do the factorisation. So I just leave it as 1 on x. I get 1 on I. That's bi minus c. Real part must equal the real part. Imaginary part must equal imaginary part. B equals minus 1, c equals 0. So it's still exactly the same idea. Right? X squared plus I, we've said, oh, there's actually 2 possibilities for this. I or minus I. So theoretically, x squared plus 1 could be factorised to be 2 linear factors. I'm not actually going to do it. So why it works is because we could, if we had wanted to, turn that into 2 linear factors. But it turns out, hey, look, they come up with the same solutions anyway, so we don't need to worry about doing that. We know that, okay, the mathematics behind it is sound, it will work. Let's just try this one here. So the first one I can do as normal. So a would end up being, I'll substitute 1 into the right-hand side, 1 squared plus 4 times 1 on 4, 1 squared, a would be 1. Okay, now this is where This method, though, you've got to be real careful, because what's going to make 4x squared plus 1 equal to 0? So I'm going to substitute in I on 2 into the right-hand side. Now, this is where maybe the other method is easier. It depends how. You've got to be careful with the algebraic manipulation, and it's going to come out. But you might want to use a mixture of methods sometimes. What do we end up with? There we go. Eventually, there's a bit of algebraic manipulation in there to come down. We've got to realise the denominator. Bang, bang, bang. But it does work. I mean, we get 1 minus 3 on 2i there. So real part must equal real part. Imaginary part must equal the imaginary part. So b equals negative 3, c equals 1. Quite possibly it would have been quicker to use the other method for that particular question. Well, what about those multiple factors? I'm not necessarily suggesting that you would use the idea, but the idea will work. So I thought, well, that's the other case. Because we looked at the linear factor, we looked at the quadratic factor, the idea works. What about when we had the multiple roots, x plus 1 squared, x plus 1 cubed, and so on? And it will work, just a little bit more work. Okay, so let's have a look at this one. So we've got a repeated root of x minus 1, and we've got the x plus 2. Now, obviously, the a is going to be easy enough. So the a is going to work out to be negative 2. The b, well, theoretically, that should be easy enough, shouldn't it? But hang on. The constant of the higher power is going to be found the same way. Okay? So when I make x equal to 1, it's not going to find b, it's going to find c. Right? So the cover-up method will work, but it will find the constant of the higher power. So say, because on the other side, you're covering up the x minus 1 squared. Okay? So you get 9, 1 plus 2, c is 3. I think the easiest way then to get the third constant is just to use a simple substitution, maybe x equals 0 and go, let's see what happens. And so I'll let x equals 0, bing, 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 and there we go, b equals 2. That's probably the easiest way of resolving the lower powers, doing something like that. Okay, let's play with this one. This was the one we had before in our example, so x plus 1 squared, x squared plus 1. So if I sub in negative 1, it's going to find b, it's not going to find a. Okay? And then for the cx plus d, I'm going to have to use I. So we get I on I plus 1 squared. So eventually we come out. Ci plus d is a half. Real part must equal real part. Imaginary part equals imaginary part. And we've still got to find a simple substitution. Again, 0 is always very easy to substitute in, so I usually pick that one. So I get a plus b plus d is equal to 0. Well, we know what a and d are, so we actually end up a equals 0 as well for this one as well. So that's the cover-up method, but expanded through to all the different cases we might see. What about a quadratic denominator that can't be factorised? Something like that. Because remember, the idea we're saying is what would make the denominator equal to 0. So the a would be easy enough to find. X squared plus 4x plus 5 is equal to 0. No solutions. Well, no real solutions. Complete the square will find the substitution you need to use. Because then it'll be like the x squared plus 1 where we can see it and just go, x is I. So if I complete the square on the x squared plus 4x plus 5, I get x plus 2 all squared plus 1. So x will be minus 2 plus I. Okay, there it is. I didn't say it was going to be easy, but it's the same idea yet again. Substitute it in, play around with the right-hand side, realise the denominator, and real part must equal real part, imaginary part must equal imaginary part. B will be negative 1. Negative 2b plus c is negative 1, so c is negative 3. All right. So in Patel, plus we've got our Cambridge, there's some exercises to have a look at.